Hey everybody, and welcome to another From the Desk of Lady Ada. It's me, Lady Ada, engineering away on yet another lovely Sunday. I had a great day today, lots of walking, getting some tasty food, tasty brunch, but now it's time for EagleCAD. Because that's how you really end a weekend. It's just sit in front of EagleCAD and just laying out a circuit. Cat's on the bed, maybe we'll show him off, so stick around. If you've been watching the last few shows, you've seen me muddle through some analog circuitry for a project called Circuit Playground. And the reason I was really tweaky about the circuitry was I wanted to make the design low cost. I kept saying well, I can use an op amp, but I really want to do a transistor here because I save 7 cents, which is nothing, right? 7 cents is it's almost nothing. But when you're dealing with a bill of materials where you really want to shave the costs, it can matter. And so I thought I'd actually take a look at the final revA. Every time I do a circuit board layout, I increment the revision. This is I used to use V1, V2, but then K-Town's no, let's do that. Let's do version number for firmware and software and stick to A, B, C, D alphabetical revisions for PCBs. And I'm down with that. So it's going to be called revA of Circuit Playground. And this is a circuit board I'm working on. Let's go to the screen and we'll take a look at this thing. What is this? What is this beast? Let's go in real close. No, okay. So here is the PCB, and we're gonna basically. What I did this morning is I finished the layout. I added that sound circuitry for the audio detector, and I also added the speaker. If you remember, the speaker we did a few weeks ago is this little surface mount speaker that I took apart, and it's not a piezo. It's actually a little wound speaker, and it's 8.5 millimeters by 8.5 millimeters. Is it great response? No, I mean it's okay. It's kind of it's really peaky at 3 and peaky at 1, but it's just for tones. I'm not going to be playing a symphony through this. Maybe some basic synthesizer notes, if I can get away with it. And we basically did up the circuit and just tested it and tested it against some Arduino code. Runs at 3 volts, 2 to 5. So I basically looked at this diagram, which is kind of mediocre, and did the layout for a basic object and kind of took a look and compared and was that's kind of what it looks like. So that was this morning. That was before brunch, and so I put the speaker right around here, and then this is that sound circuitry. But we have a bunch of other stuff here. So I thought, I actually did DRC on this, but let's go to schematic and clean up the schematic, because schematic is kind of all over the place. You can see it's I started over here and then I kind of went all over. Mostly because the project got bigger than I expected. I started with the Flora schematic, and I basically pulled stuff out to make this. So let's first make this frame bigger, because I'm certainly going to need this. And some people are well, why don't you just have another sheet? I don't really do that. I usually just use one sheet, and I maybe will make it a little bit larger. So I think I was using frame. Let's maybe do an A4. Ugh. It's a gate. Oh no, that's smaller. I don't even know this European. Yeah, there you go. It's a little bit bigger. European frame sizes. Get that out of here. I think that'll probably fit most everything. Okay, so let's start with the microcontroller. So for the microcontroller, I'm using, let me smash this, smash. I always lose the smash symbol. Smash. I'm using an Atmega 32U4 MU, so it's a QFN, Atmega 32U4. And this is, you know, your basic Arduino compatible with USB built in. It's got 32K of flash, 2.5K of RAM. You know, that's not a lot compared to, say, like the SAMD21 that I was playing with earlier. But, you know, it's good enough for what we want to do, and that's basically just make a basic low-cost all-in-one board. And so let's just tuck this. So yeah, it says like Flora, because this was Flora. And put that here, and there's my little notes. So this has a native USB circuit, so you can see over here there's a USB micro B. But I'll just, I'll tuck that over here. What drives me crazy is, like, for some reason, I guess when we made this object, the D minus and D plus are swapped. I might want to make this a little bit nicer looking by splitting this up, cutting this, naming this D minus, this D plus, this D plus. Yep, connect it, and then I'll actually cut this. I'll have to reroute those signals, but that's fine. This is D minus, and this is D minus. And then this actually is like in the power circuitry area, so I'm going to move this guy over. Oh, and funny, it says the value is a mini USB. This is definitely not a mini USB. This is a micro B USB. Okay. Okay, so I can kind of move this in, move that in. So you got your microcontroller. It's 8-bit. I'm running it at 8 megahertz off of this ceramic oscillator. If you're picky, you're probably like, hey, you know, you're not really supposed to run USB client devices off of a ceramic oscillator. You're supposed to use a crystal. And I'm like, yeah, you know what? That's true, but the failure rate we've seen has been like near zero. Like, I don't even know that I've ever seen a board fail under test. We do under test a full USB bootload, so we can make sure the USB interface works. I've never seen it fail due to the crystal. Again, it's like, am I designing this to go to space? No, I'm designing this to be used in classrooms where the ambient temperature is going to be 25 degrees C. So I'm cool with sticking with a ceramic oscillator. They're nice and small and cheap, and they're stocked. And then what's nice is this has a whole bunch of analog digital converters. These are all ADCs. There's actually more ADCs here. This is an ADC. This is an ADC. This is an ADC. And then up down here, there's a couple more. I think ADC 8 is down here, ADC 10. So it's got like 12 ADCs or something crazy, or 10. You know what? This does not have to be ground, but I can change that later. And yeah, so it's got USB. I run off of 3-volt logic. This does take 5 volts in here. This is the V bus. This is just for detecting when the USB is plugged in. So let's tuck that whole thing over here. And then this is a thing that K-Town has taught me that I'm kind of into. He uses a short dash and just makes a nice little cove for this, and then you can label this at Mega 324 Microcontroller. Bam. Okay, well, cool. All right, so let's go to the power section, because I think that's an easy one to do. So power is this circuit and this circuit. And let's just kind of get these labels all cleaned up. Go over here. Oh. Turn off the short dash. Otherwise you're like, why is my wire not connected? We've got 2 Schottky diodes, and Schottky diodes are kind of pricey. Like the ones I'm using are 6 cents each or so, but they're worth it. And they're worth it because I really want to have flexibility with power. On the main board, we've got USB, and I want people to be able to connect via USB. You plug in the micro USB, the board powers up, and it's good to go. And I also want it to be plug-inable via the JST jack down here, which is it's a LiPo battery connector. And I don't know precisely what, actually VBAT, I want this to be 3 to 6 volts. Talk about why later. I really don't want to, even if battery is plugged in, even though, it tends to be smaller than the USB. If it was always smaller, then I wouldn't have to worry about it. But what if this is 6 volts because somebody uses like 4 AA batteries? Then VCC could be, if this was connected, it could be higher than 5 volts. I don't want that back feeding to USB. So I put in 2 Schottkys, and they're about 0.2 volts drop, and that's cool by me. I do need them to have 1 amp current. I know this, but I feel like why not document it? I also can't spell Schottky. I think it's spelled wrong. I can never remember how to spell it. It's like, is there an E in there? I don't even know. Sorry, Schottky. I mean, he was a fellow, and I feel bad for the guy because I can never really spell it. Okay, so 3 to 6 volts, actually it should be like 3.5 to 6 volts, comes in here, 0.2 drop, goes to VCC. Likewise, from VBus, you get this 5 volt. That 5 volt, remember, goes to the microcontroller, which detects whether the USB is plugged in. This way it doesn't, by accident, think it's plugged into USB if the battery is plugged in, because there's a blocking diode here. Also to VCC, and then VCC basically just goes into this regulator, and this is a 3.3 volt regulator. Make this super clear, and then there's this tap. Talk about that a little bit later, but so this is 3.3 volt, and VCC basically can range from 3.5 to 6 volts. So it's a non-stable voltage. It's V high, but what we really want to just have everything on off of 3.3 volts. And so this is 3.3 volt regulator, and then question mark milliamp, because we haven't set our power budget. Well, I have in my head. And then we also have these taps. And these taps are around the board, and they're basically access to 3.3 volts and ground, and then VBAT, which is actually VCC, and ground. And so you have access to these voltages if you want for access to power and ground if you want to connect alligator clips and such. So that's power, and then I have a bunch of, I got my capacitor bank over here. I'm going to stick that with power. Let's see, maybe. Bring this down a little bit, and then label this USB power data down here, and this is JST battery in over here. This is 3.3 volt regulator, and then I can tuck these down here. And actually, now that I think about it, I'll cut this and I'll lay this down over here too. And move these over here, so we have all of them sitting in one place. Okay. You can be neurotic forever on this. Okay, and then we've got our capacitors. These are probably going to tweak a little bit. Like I think I'm going to go for 1 microfarad. They're the same cost as the 0.1, and I don't have a ton of capacitors on here, so I'm like, I might as well put plenty on the 3.3 volt line. Basically, I have 1 10 microfarad next to the regulator, and then I have sprinkled 1 microfarad around the board. It's not a lot, but I think it'll be okay. We'll see in production whether it really matters. If so, I actually have a little bit of space. I could probably drop another 2 or 3 capacitors. Like, this isn't a single board Linux computer, so I think it's going to be okay. Okay, so here's my capacitors. I'll put them over here. And I think that's it for the regulator section. So, boop. And then power supply. Okay. So we got this Atmega 3G4 and you got a power supply. Great. So like you're like, so what? So what? What's the big deal? So the idea here is this Atmega microcontroller here. You have a micro USB jack up here and a battery jack over here, and then here's actually that Schottky regulator area. You can kind of see, you know, this USB power snakes all the way around with a nice thick trace, comes in here, feeds into this little regulator, little very small regulator, and gives you 3.3 volts. You have the microcontroller, and then instead of just being like a Feather or like an Arduino, which is an excellent idea. You know, the Arduino comes with, even the Leonardo Micro comes with the battery, you know, power supply, basically like so. You know, the crystal that you need, you know, a reset button. Can I select the reset button? Is that, were you going to let me? There. Reset button over here. You know, maybe a power LED and a pin 13 LED. But I actually wanted to make a board that had kind of like everything in it. And that's why we call, the working name of it is Circuit Playground. The idea is that instead of just having a microcontroller board that like you plug in stuff and you're like on a breadboard and it kind of has everything but nothing at the same time, it's like the kind of the bare bones. I wanted to make something that was very full featured and had a lot of stuff. So you know, normally I would just stop with like, okay, I got the USB, like if you look at, for example, the Feather 324, which is kind of what this is based on. You know, you've got your microcontroller over here, your regulator, a power supply, JST, micro USB, same deal. A Schottky diode. It has a little battery recharger and a reset button. But basically it's the same thing. It's much smaller, but you don't get anything else. And so we took this and we're like, okay, well, let's see how much we can cram into 2-inch diameter space. That's pretty much what we thought. We were at brunch, probably, or lunch or dinner or something, and we're like, hey, let's just cram as much as we can possible. So in addition to the functional core, we also added a light sensor and a temperature sensor over here. This is temperature, this is light. There's 2 buttons. There's a left button and a right button. And these are just tactile. They're not large, but they're big enough for most hands. They're not as small as the reset button. That's for a little teeny mini button. This is a LIS 3DH triple axis accelerometer. Actually just put in the breakout board into the store. All these actually kind of came in as breakouts first, just to get a sense of it. And what I really like about this is accelerometer is it's a pretty good accelerometer and also has tap detection. So if you like tap it or double tap it, it can actually detect that and give you an interrupt. So that's kind of cool. And it also has like free fall detection and can do like tilt analysis. It does quite a few things built in, and it's pretty cheap. And then in addition to the two buttons, down here we have that MEMS microphone with a little amplifier circuit. And this isn't for like high fidelity audio. It's just to do like basic audio volume, and then maybe if I do this right, we can do some very light FFT work. So you can kind of get frequencies out and maybe have stuff react to the frequency. There's a switch. Now instead of having an on-off switch like the Flora does, the Flora has an on-off switch over here, I think, on the left-hand side. This isn't an on-off switch. It's actually just a usability switch, just left or right. You can flick it and it will set a pin high or low. I decided to drop the on-off switch because I thought that while it's very, very useful, I wanted to instead pack it with a battery pack that had, I'll show the battery pack. Yeah. The AAA battery pack with on-off switch. It has an on-off switch on it, and so I was like, well, if you have it plugged into USB, you're not going to turn it on and off because it's plugged in. And if it's on battery, you're going to use a battery holder with an on-off switch. And I kind of decided, like, I have to make a trade-off. I could put an on-off switch, but basically I don't get to have a usability switch instead, like a user switch. So I went with the user switch instead. And then that speaker. And then here is the diode and transistor driver for the speaker. So just a basic buzzer, makes tones. And then around the edge, I have these mini NeoPixels. So this is a new product that we're about to put in the store. And it's the SK68 one. No, let's see. Hold on. Let's see. Mini NeoPixels. Basically, this is it. It's not live in the store. You can see the price is $0, but compared to normal NeoPixels, it's much smaller. So, but it's the same basic chip. Like you can see, like, hey, this chip here is over here, and then it's just like squished. So this is 3.5 millimeters by 3.5 millimeters instead of 5 by 5, and that extra size difference actually does make it possible for me to basically cram 10 in here. So you get 1, 2, 3, 4, 5 on the right-hand side, and then 1, 2, 3, 4, 5 on the left-hand side. So you get 10 RGB LEDs total in ring-like-ishness. I mean, like, you don't get a ring at 12 o'clock and at 6 o'clock. You just get 5 on each side. But I think, like, you can still do, swirly effects, and it'll mostly look like a ring. Just kind of like, it wasn't possible to squish in. Like, this space just got too busy, and this space got too busy to make it completely evenly spaced. And then, like the Flora, hold on. Actually, it's 659. Oh, site's being sluggish. Okay. The Flora has these pads on the outside. It has 1 NeoPixel. This is kind of my experiment of doing that. It has these pads on the outside, and I made the holes for sewing, like specifically for sewing into clothing and stuff. And for this board, I actually did something slightly different. I have the same kind of pads, but they're larger, the holes are much, much bigger. And these holes are large enough that you can fit alligator clips in. So I gotta just route these lines again. These are the D plus and D minus that I cut earlier. So, oh, sorry, this is supposed to be bottom. Okay. And then, if anyone knows how to make it so the drill for vias is default round and a different size, let me know, because I can't quite figure out how to make that default. And I kind of do it 18 times a day. That would be great. Okay, thanks. Okay. So actually, I'm going to show the large holes because the thing is this is like my new trick. Like, I've been doing this for like 8 years, 9 years, whatever, 10 years more-ish. And I'm always learning new tricks. And my new trick is I use a really awesome 3D rendering engine to look at my boards before I send them off. And it's totally like I've learned how to look at Gerbers, and I can kind of like, I see it, I know what it's going to look like. But if you're not really into that, check out this cool trick. So I'm going to process the Exelon.
This is the first time probably anyone has ever done this live.
What, generating Gerbers?
On the internet.
By the way, we call dibs on calling our next cat Gerbers. You can't have it, viewers on the internet.
Yeah.
Gerbers is ours.
But this 3D thing, no one's ever seen this before.
Okay, so, sorry, let me close, like, I have 5,000 things going on. This is schematic I was just working on. I don't really need this anymore. Okay, so, yeah, so I already have a folder on my desktop. That's just my thing. Go back to Circuit Playground, revA. Let's get rid of all my hash bits. And you'll notice I use Git for everything, even hardware. Works out. And then I don't have a bottom cream layer. I don't need the GPI. So I've got dimensional layer, the drill layer, bottom copper, bottom overlay, bottom stop, top copper, top layer, top overlay, top stop. And then I swear this is called 3D Gerber Viewer, but the name is Zoff's PCB, and this one is like the best one. And you just have to tweak it so that it you make a rule set and it knows the name of the 3-letter postfixes for all your file names and what they mean. So like DIM means board outline, and DRD means drill, and GTC means paste mask. I have like my own personal desires for what I want to call them. Like, I know that these are non-standard. I just use GKO sometimes, but I like DIM because I always had board houses that were like, which one is the dimension layer? And eventually I was like, fuck it, I'm just going to name it DIM. Okay, that's the dimension layer, DIM. Anyways, so auto-load this. And it does this cool thing, and it basically renders your circuit for you in 3D, and then you can like spin it and stuff. So you can see I still have my Flora silk on the bottom. So this is actually not FCC&C, and it's not revB. I gotta change that before I finish. I got my programming pads up here. So when I put the board in for production to test it, I will use these pads. This is like reset, mostly MISO clock for SPI. Yeah, so those 4 pins, and then I'll get power and ground from these pads over here. I got the USB, and I've got tons of nothing on the bottom. Bottom is free and clear. So I'm going to probably put maybe instructions or like a basic tutorial, like when I download instructions for this. So it doesn't have renderings of the components, and that's okay, because at this state, I'm mostly just, I kind of know like what the components look like. I'm like, okay, this looks like an LED, and this looks like a micro USB. Would it be cool to integrate that? Yeah, I'm totally don't feel like rendering all the components or figuring out how to get the rendering shape in. For me, I don't need it, but feel free to if you're totally into it. And what's nice is I can also change the color looks, because if I'm trying to decide what colors I want, so like Osh Park, It's purple. Adafruit black. Black is actually, it's very, very dark green because you do see a little bit of the traces anyways. But it kind of gives you a sense of what it will look like. And Adafruit blue, so you can change this with the color picker. So you can change the background, or you can change the silkscreen. Let's say you're like, I'm going to have some crazy, yellow silkscreen or something. I don't know. You can try out yellow silkscreen. My silkscreen's always white though. And then the solder mask, of course, if you're like, okay, maybe we're going to get this done in a purple color or a red color. And anyways, I like it. Wait, I don't want to save this. I'm just going to close. But this really gives me because the traces, I see them and I see the vias, I can when I look at the circuit board, I actually get a better sense of because when you're looking at it in EagleCAD, the green vias really stand out. And it's important when I'm doing the layout because I want to make sure that they're spaced properly and I don't have too many, and it'll help me spot them. But when you're looking at the volume of it, sometimes the green vias to me seem like they're elements on the circuit board that are exposed, but they're actually tinted. So this shows you look, the vias are tinted. You actually have quite a bit of silkscreen space available here and here and here and here. And down here, I could probably even fit another component or two if I wanted to. But anyway, what I wanted to show is, and you can turn off the paste if you want to see. The paste is the, I did this once. I don't know what happened. I kind of broke it. Don't double click on stuff like I just did. I want to reload it. Whee! What I want to show is the big holes in comparison to a Flora, which has these little ones. These ones are large and you can fit alligator clips through. And what this is actually a lot like is the MPR cap capacitive. It's kind of the same idea here, where I have these big holes, and then you can clip alligator clips into it. You can see here, you just clip the alligator clip here. Here I have two holes, so the alligator clip grabs onto both. On here you would just have the alligator clip onto the end, and it would just grab it, and that would, whoa, that was cool. Oh, you know what? That's that's showing me the depth. Oh, that's cool. Whoa. Whee. Okay. That's neat. You can see just the copper layer, and then I guess if you have 4-layer board, it's really handy. It's the bottom layer, just the bottom layer, bottom silk screen. Okay, so I like this program. Anyways, my recommendation. Hopefully it's useful. Okay, so back here. So I think the 2 buttons. We have 2 buttons: speaker, sound, light, temperature. 10 LEDs, battery, doesn't have an on-off switch, but has a switch. I didn't put a trim pot on, and it was kind of a decision of a potentiometer. It would have been really cool, and I'm not against at some point redesigning this to have a potentiometer, but I didn't quite have space. I really wanted to have sensors on there. I thought accelerometer was worth it. If I had to, because I could have put a potentiometer here instead. Just had a through-hole potentiometer that you twisted. But I thought an accelerometer was interesting enough that it would be worth it to trade a potentiometer for an accelerometer. I also thought, I could put a little mini trim. The thing is, having a surface mount, you can't really have a surface mount potentiometer unless it's a little trim pot. And then you have to include a little screwdriver. So it wasn't really worth it, in my opinion.
Okay, let's do one question.
Yeah, let's do some questions.
Someone wants to know if you can export that as a 3D file format from that program. So repeat your question.
Okay, so the question is, can I use 3D Gerber Viewer and export this as
Some type of 3D
a 3D file? That's an excellent question. I have no idea, but let's find out if it has anything that will let me export. I don't think so. I think it's just a renderer. However, if you would like to export, you can use a ULP. And there is, I don't know if it's included here. Yeah, here it is. Generate 3D data. So you can export that if you'd like and use that to generate a 3D file. I used to generate 3D models with Pavre, which is a free and I think open source 3D rendering program, and it's really cool. It's just the reason I tried Zoft's PCBs because I don't need the component. The cool thing about Pavre is it'll model the components as well. So I think if you search for Pavre Eagle 3D, click on images, so you can see you can get really sweet renderings, but you kind of have to have all these in a library, and I don't, and I'm not using through-hole parts, and these are so cool, but I just don't really need them. Yeah, these are super cool, but I just this is awesome, but it's just not something I need because I know how tall everything is. I need a vision of what this screen looks like. That's kind of what I'm checking for. I think we'll get a purple PCB.
Last question.
Okay.
How do you make the pad so big?
How do I what?
Make the pad so big.
So how do I make the pad so big? So it's a bit of a hack. So in the library, sorry, let me see, what was the name of this again? This was called SOTAP/alligator. Oh, whoops, sorry. Click on the thing. SoAlli, okay. So what you do is you create the pad, which is the actual through-hole pad. It's a through-hole piece. You just make the drill as big as you can, or as big as you need. In this case, it's an 1/8 of an inch, and you can set the diameter however you want, and then you draw this using the polygonal tool. You draw the top and bottom layer to create this sort of the oval shape. And then you also need to add a stop layer as well, because it's not a true pad, right? It's not an actual, this isn't a true pad shape, it's faked. It's actually a round through hole, and then you put a copper around it to make this sort of nice oval shape. And as far as, you get errors, but then you just kind of deal with it. So if you run DRC, you will get, and you don't see this because I approved these, dimensional layers. You get width complaints a lot because it's hey, this isn't really a trace. But, I use this on the floor and it's fine. You just have to be okay with, just I have an oval slot here on the micro USB and I get dimension complaints. And you're just okay, I know what these are. These aren't true DRC problems. This is just because the pad is going all the way to the edge. So that's that. So, can I just show one last thing before we head out? So this is sensor number 1, and this is the List3DH. And in this case, I'm using SPI. I'm using SPI for this because the I2C pins, I'll tell you in a moment, they're going to be used for other things, and I also want to keep them available. So even though I could have put this on I2C, I ended up putting it on SPI, which is fine because I have a library code for that. This is the 10 neopixels, and I'm going to ended up changing the order of these. That's why this trace kind of goes out in a weird way. So let's just clean So we got 10 neopixels. And this isn't a WS2819. This is actually an opto. This is a SK6812. And these actually run fine off of 3.3 volts. So I'm running them off of 3.3 volts. Now you're probably saying like, hey, wait a minute, white and blue LEDs, blue LEDs and also white LEDs have a forward voltage of 3.4 volts. Don't you need to have it be higher than 3.4? If you wanted to have like perfect color reproducibility, but I actually don't care. And I've also noticed that at the currents that the neopixels get driven at, 3.3 volts is fine. Like you get all the color that you want from them, and those are driven from a line. So it's 3.3 volt, and the neopixels are driven from 3.3 volt. We have a light sensor. So the light sensor is a basic photo transistor, and basically, light hits it, and then current goes through, and then the more light you have, the smaller this resistance, so the light sense analog line starts lifting up. So it's kind of, it's a little bit more intuitive than having it on the bottom, because it's like more light is a higher value. Likewise, for temperature sensor, I decided that since I'm going to have a library to hide all the details, that I would go with, instead of a sensor that does all of it for you and you just read the analog voltage and you get an analog voltage that's proportional, it's going to be a thermistor. So you have a thermistor divider, and then I'm going to basically have a library code that just does the conversion. And then on the last two items, this is that speaker that we did a while ago. It's just going to be a buzzer, square wave in, square wave out. And then finally the microphone, which is just going to give us audio volume. So MEMS mic output, little amplification, also into an analog pin. And that's pretty much it. I got the buttons. Over here, I got the switch, which is just 5-volt ground, and then I have a switch pin, and then 2 LEDs. So the idea here is it's got kind of everything you want, hopefully, and be able to sell this for like maybe $20, $25. And what I'm trying to solve is we have schools that contact us or company groups, and they want to do a hackathon, and they're like, we have 1,000 people and they all want to take part, but they can't learn Arduino in time. Like, it's going to be a 2-hour hackathon or a 3-hour hackathon, and they can't learn how to do breadboards. They basically have to have something where they plug it in and they're ready to go without wiring, maybe some alligator clips, but you can't have soldering involved. And so this is, what can we fit into a 2-inch circle? Something that can maybe be used for wearables, something that's portable, can be run from battery power, that can do this. So I think that this is going to be pretty good. I'm going to fix that back silk, change the version number, and I'm going to send it out for prototype. Maybe in about a week, I'll get those PCBs back and put them together. Whew, that's it. Yeah, unless there's more questions. Do a little jig. Do you want to show the cat? I can grab the cat.
Yeah, you can stay there.
I feel like cat was promised. Oh man, he is not so pleased.
It's the question you like last
All right.
I do the audio video on the animal
Thanks. Yeah, you were the animal wrangler at
handler. Yeah, I'm an animal handler.
Yes, from here. Okay.
Yeah.
Say goodbye, Mossfet. Goodbye.
Is that it?
Bye, everybody.
Okay.